Neural Network Fundamentals and Deep Learning Architectures. Introduction. Think about how effortlessly you recognize a friend's face in a crowd, or understand a sentence someone just said to you. Your brain does this in a fraction of a second, using billions of interconnected neurons working together. For decades, researchers have tried to borrow that same idea and build it into machines. The result is what we call artificial neural networks, and today they form the backbone of almost every major breakthrough in artificial intelligence, from the recommendation engine that decides what show to suggest next, to the vision system in a self-driving car, to the language model answering your questions. In this video, we're going to build up neural networks from the ground floor. We'll start with the smallest building block, a single artificial neuron, and work our way up to two of the most important architectures in all of deep learning, the Multilayer Perceptron and the Convolutional Neural Network. By the end, you'll understand not just what these models are, but why they're built the way they are. Neurons, the building blocks. Every neural network, no matter how large or complex, is built from the same basic unit, the artificial neuron. Just like a biological neuron receives signals, processes them, and decides whether to fire, an artificial neuron takes in some input, usually the output of other neurons before it, applies a mathematical operation, and produces an output. The key piece that decides whether the neuron fires is called an activation function, which we'll dig into shortly. For now, just picture a neuron as a tiny decision maker. It looks at whatever information is coming in, weighs it, and passes along a signal based on what it sees. When you connect thousands or millions of these tiny decision makers together in layers, you get the rich, flexible behavior we associate with deep learning. Perceptrons, the simplest neuron. The perceptron is the simplest and most fundamental type of neuron, and it appears inside virtually every neural network architecture in some form. Each perceptron has its own set of weights, one weight for every input it receives, plus a single bias value. When data flows into the perceptron, it multiplies each input by its corresponding weight, adds all of those weighted values together, adds the bias, and then passes the result through an activation function. You can think of the weights as how much attention the perceptron pays to each input, and the bias as a kind of built-in adjustment that shifts the result up or down regardless of the inputs. These weights and biases aren't chosen by a person, they're learned automatically during a process called training, which we'll cover in a later video. For now, the important idea is this. A perceptron is a tiny calculator that combines its inputs in a weighted way, and every one of those weights is a dial that gets carefully tuned so the whole network produces accurate predictions. Activation functions, adding nonlinearity. Here's a subtle but crucial point. If you strip away the activation function from a perceptron, what you're left with is mathematically identical to plain linear regression. The weights act like coefficients, and the bias acts like an intercept. A model like that can only draw straight-line decision boundaries between categories of data. But most real-world problems aren't that clean. Think about separating cats from dogs in a photo, or fraudulent transactions from normal ones. The boundary between these categories is almost never a straight line. This is exactly the problem activation functions solve. By introducing nonlinear behavior into each neuron, activation functions let networks bend and curve their decision boundaries to match complex, real-world patterns. And because these nonlinear operations get stacked layer after layer, the network as a whole becomes capable of representing extremely intricate relationships in data. Let's walk through the most common activation functions you'll encounter. The sigmoid function squashes any input, no matter how large or small, into a range between 0 and 1. It behaves almost linearly for middle-range inputs, but flattens out towards 0 or 1 for extreme values. The hyperbolic tangent, or Tanh, behaves similarly to sigmoid, but stretches its output range between -1 and +1 instead. The rectified linear unit, or ReLU, is today's most popular activation function. Its rule is refreshingly simple. Any negative input becomes 0, and any positive input passes through unchanged. The Leaky ReLU is a small tweak on this idea. Instead of forcing negative values all the way to 0, it lets a small fraction of the negative signal through, which can help avoid certain training issues. Finally, the Softmax function is special because it doesn't operate on a single number. It operates on an entire vector of numbers at once, converting them into a set of probabilities that all add up to 1. This makes Softmax the go-to choice for the final layer of a classification network, since it lets us say something like, "There's an 80% chance this image is a cat." Neural network architectures, blueprints for organizing neurons. Now that we understand the individual neuron, let's zoom out. A neural network architecture is essentially a blueprint. It defines how neurons are organized into layers and how information flows between those layers. Different architectures exist because different problems call for different structures. Some architectures are great with tabular data, others excel with images, and others are built specifically for sequences like text or time series. One key concept is depth. The more layers a network has stacked on top of each other, the deeper it is considered to be. This is where the term deep learning actually comes from. Models with many layers, capable of building increasingly abstract representations of data as information passes through each successive layer. In the next two sections, we'll explore the two most foundational architectures in deep learning, the Multilayer Perceptron and the Convolutional Neural Network. The Multilayer Perceptron, MLP. The Multilayer Perceptron, or MLP, is the most common and foundational neural network architecture. It consists of 3 types of layers: an input layer, one or more hidden layers, and an output layer. Every layer is made up of the perceptrons we discussed earlier. Data enters through the input layer, flows forward through each hidden layer in sequence, and finally produces a result at the output layer. Each perceptron in a hidden layer receives the combined output of every perceptron in the layer before it. This is what makes it fully connected. As the training process unfolds, the weights and biases throughout the entire network are gradually adjusted so the model's predictions get closer and closer to the correct answers. Let's make this concrete with a classic example, classifying handwritten digits using the well-known MNIST dataset. Each handwritten digit is stored as a small 28 by 28 pixel grayscale image, where every pixel has an intensity value between 0 and 255. Since an MLP can't directly accept a grid of pixels, we flatten that 28 by 28 image into a single list of 784 values, essentially unrolling the grid into one long line of numbers. Each of those 784 values becomes one input feature for the network. To label the correct answer for each image, we use something called one-hot encoding. Instead of just saying, "This is a 7, we represent the answer as a list of 10 numbers, all zeros except for a single 1 placed in the position corresponding to the digit 7. This format works especially well with the Softmax output layer we described earlier. For our example network, we might choose 3 hidden layers with 64, 128, and 256 perceptrons, respectively. These choices, along with the number of layers, are called hyperparameters, and they're typically selected through experimentation. The input layer will always need exactly 784 perceptrons, 1 per pixel, and the output layer will need exactly 10 perceptrons, 1 per possible digit. We'd apply the ReLU activation function throughout the hidden layers and finish with Softmax at the output so the final results can be interpreted as probabilities. The digit with the highest probability becomes the network's prediction. Convolutional Neural Networks, CNN. While MLPs are powerful, they have a real weakness when it comes to images. Flattening a 28 by 28 image into a single line of 784 numbers throws away all the spatial relationships between neighboring pixels. Convolutional Neural Networks, or CNNs, were designed specifically to preserve and exploit that spatial structure, which is why they're the dominant architecture for image classification, object detection, and image recognition tasks today. At the heart of a CNN is an operation called convolution. Picture your image as a large grid of pixel values. Now imagine a much smaller grid, called a kernel or filter, sliding across that image, one small patch at a time. At each position, the kernel multiplies its values against the underlying pixels, sums up the results, and produces a single number. As the kernel slides across the entire image, left to right, then down and left to right again, much like reading a page of text, it produces an entirely new grid of numbers called a feature map. The distance the kernel moves at each step is called the stride. A convolutional layer typically contains many kernels, not just one, each learning to detect a different pattern. One might learn to detect vertical edges, another horizontal edges, another particular textures or curves. As you stack more convolutional layers deeper into the network, the patterns being detected become increasingly abstract, starting from simple edges near the beginning of the network and building up to complex shapes and object parts deeper in. After convolutional layers, CNNs typically apply a pooling layer, whose job is to shrink the size of the feature maps while keeping the most important information. The most common form, max pooling, looks at small patches of the feature map, say a 2x2 block, and simply keeps the largest value from that block, discarding the rest. This makes the network more computationally efficient and more robust to small shifts or distortions in the input image. After several rounds of convolution and pooling, the resulting feature maps are flattened into a single vector and fed into fully connected layers, essentially the same kind of layers we saw in the MLP, which make the final classification decision. Let's revisit our handwritten digit example, but now with a CNN. This time, we don't need to flatten the 28 by 28 image at all. It's fed directly into the network as a grid. We might design a CNN with 2 convolutional layers. The first with 32 kernels, the second with 64 kernels, each kernel sized 5 by 5, with a 2 by 2 max pooling layer following each convolution. After the second pooling layer, the resulting feature maps are flattened and passed into a fully connected layer of 128 units, which then feeds into the final output layer of 10 units, 1 per digit, using Softmax, just like the 4. Other common neural network architectures. ML, Ps, and CNNs are foundational, but they're far from the only architectures out there. One of the most important alternatives is the recurrent neural network, or RNN, which is designed specifically for sequential and time series data. Think of a stream of sensor readings taken over time, or the sequence of words in a sentence. Unlike MLPs and CNNs, which process each input independently, RNNs have a kind of memory. Some of their outputs get fed back into the network and combined with future inputs, allowing the model to carry context forward through a sequence. RNNs have inspired several important variations, including long short-term memory cells, gated recurrent units, and transformers, the architecture behind many of today's large language models. We'll dedicate an entire future video to exploring these sequence-based architectures in depth. Beyond RNNs, there are other specialized architectures, such as restricted Boltzmann machines, Hopfield networks, and deep belief networks. While we won't go deep into these today, it's worth knowing they exist, each suited to particular kinds of problems, and each differing in the specific mathematical operations and training procedures they use. Summary. Let's bring it all together. Every neural network, no matter how sophisticated, is built from the same basic ingredient, the perceptron, which combines weighted inputs and a bias, then passes the result through an activation function to introduce the nonlinearity needed to solve real-world problems. From there, we organize perceptrons into layers to build architectures. The multilayer perceptron connects every neuron to every neuron in adjacent layers, making it a flexible general-purpose model, while the convolutional neural network uses sliding kernels and pooling to specifically exploit the spatial structure found in images. We also got a glimpse of the broader landscape, recurrent neural networks and their descendants, built for sequences rather than static inputs, along with a handful of other specialized architectures. In the next video, we'll finally open up the black box and talk about how these networks actually learn, the training process that tunes millions of weights and biases until the network gets good at its task. If you found this breakdown helpful, consider subscribing so you don't miss it, and drop a comment if there's a specific architecture or concept you'd like to see covered in more depth. Thanks for watching, and I'll see you in the next one.